I'm Bryan Acosta, and I'll be doing question 29.
All right, question 29. The following reaction establishes equilibrium at 2000 Kelvin. Nitrogen plus oxygen equals nitrous oxide. Okay, so from here, it also gives us if the reaction begins with 0.1 moles per liter of nitrogen and 0.1 moles per liter of oxygen, what were the equilibrium concentrations of this species? And also gives us our our equilibrium, or our Kc constant of equilibrium. So from here, I just wrote down everything it gives us, the initials. So we're going to start. So our formula, this is clearly a ice problem. We're going to start out with the initial, the change, and the equilibrium. That's why it's named ice. So you're going to come over here and you can see I pretty much set up a little mini table with each element just listed up on there. And then I wrote some basic formulas. So this is the Kc formula right here, the concentration of the products over the concentration of the reactants. And then whatever is the coefficient, it actually becomes an exponent in this case. And okay, so we're gonna go and start. So nitrogen, initially, they tell us we have a concentration of 0.1 moles per liter. So I just put all their initials in here. And since this is initial, the reaction hasn't happened yet, which means that 2NO is 0. The initial, it hasn't even happened yet, so there's none. All right, so our change, it means it's going to be minus X. We're going to take an X amount of this element and an X amount of this element to form 2X worth of this. Why is that a 2? Because we have a coefficient of 2 out front right here. And due to our molar ratios and everything that we learned a couple units ago, we know that's a 2X. So doing that, the equilibrium will just be the initial minus, or the combination of these two, which is just initial minus X. And then, as you can see, just basic math right there. All right, that's our equilibrium. From there, we're going to plug in what we know into this equation. So we know that the equilibrium of NO is 2x squared. We plugged in these values we got over here into this, because this is the concentration at equilibrium of nitrogen and oxygen. And then we plugged in our Kc, or our constant, right here. So from there, I also showed some simple algebra moves just to make it a little bit more easier to read, simplify it a little bit, but pretty much you just, let's see here, that should actually have some brackets on it, because I haven't simplified that. But yeah, as you can see, this formula is the exact same as this one, so it's just that squared. Now this is the part where I go over some sort of little, it's a shortcut that we learned in class. Because since this is actually see, you can tell by these double arrows, and that we're having a weak, or it's not completely dissociating or associating into one. Just by seeing this notation, this means this one arrow means that we're going to fully transfer over, and this back arrow means that there's also a reverse process going on at the same time. In doing so, we can actually neglect this X on the bottom. It's part of our shortcut, right? And doing so will leave you with this. I'll also explain why we're doing that and a little bit how we can do that. So if you're a little bit confused right now, then no worries. I went ahead and just this used to be 2x squared. I went ahead and just squared everything for x squared over. And then since I neglected the x, this is just 0.100 squared. Did some basic little math here and I got this part, right? From here, multiplied this over to this side, which you can see this is the response right here. This is what happens. And then divide by 4 to get this number and take the square root, and that's our x. Now back to when I said we were going to neglect the x. In order to check if it is possible for us to neglect the x, it means that we have to do something called the percent dissociation check. Pretty much the percent dissociation of this has to be of negligible magnitude. So you do that by doing our absolute value of our change over our initial quantity. So x, as you can see in our ice chart, the C for change, x is what is in there. That is the change, pretty much. And since we're neglecting the x for the equilibrium of these two, right, you can see it'll focus, okay? Neglecting the x of these two, Then we're gonna put in our change, which is the x, into this change slot and take the absolute value of it, and then our initial quantity, which is the 0.11, or 0.1 it was described in the problem, times 100 to turn our ratio into an actual percentage. So there's a percentage, and the rules for the check is as long as it is less than or equal to 5%, then we are able to take our little shortcut and neglect the x. All right, so hopefully that all made sense. I'm also going to show you another method of finding the x value without neglecting the x. If, let's just say, if you forgot how this shortcut works, or if you just want to know, then I'll do that, but that'll be towards the end of the video. We still have another portion to finish here. So looking at our elements and everything, the original question asked us on part 2, I believe. Is it part 2? No, it's just all one. So what were the equilibrium concentration of all species? So the concentration of nitrogen at equilibrium is equal to just what we showed over here in our ice chart, right? We found our x, we're going to plug it in, and we're going to basically solve for every value. So equilibrium of nitrogen, the concentration of nitrogen is just initial minus x, and then oxygen, initial minus x, and then 2 times x for that, and this is all your things. All right, from here on out, if you're okay with just doing it just based on the shortcut, that's good, but I'm going to go ahead and show you the normal way to do it without the shortcut. All right, so just going back to this part of the problem here, when we plugged in everything we knew for our Kc formula, and basically from this point onward, it's just really math heavy, because our shortcut just allowed us to get rid of this x, but now we can't necessarily do that, so we just solve everything algebraically. So since these are both squared, just basic math, you take the square root, and you have to account for now the plus and minus of our value. Kc was given, because when you take the square root of something, you have to account for both plus and minus. So from then on, we can just come over here in this section, and I wrote it in as 2 columns, one for the minus and one for the plus. And if you feel free to pause and just see what's going on here if you don't necessarily understand. But basically I just go through step by step and use algebra just to simplify it down to get an answer. And you might ask yourself, okay, I have a positive and negative, but that's 2 answers, like they can't work for our problem, and you would be right. Because if you look at this value, which is negative, that actually won't work, because our change has to cause there to actually form a concentration for each value. If you look back at your chart and you look and see, I believe it was 0.1 minus x and other values such like this, right? That if you actually made it so that it was negative, it wouldn't work. So that's how you just using a little bit of logic and looking back at your equations, we'll be able to show you that the positive is the right one. And if you actually compare this back to what I got in the original with the shortcut, it's extremely similar. So yeah.